new season of the colloquium. And I first would like to apologize. Given this, position as a colloquium organizer, very late. So we had to delay the first 2 weeks. I already didn't have a colloquium, but hopefully we'll now have a colloquium on a regular basis. I also approached some of you already for colloquium for the later stages of the year. But in any case, let us begin. So today we have our first colloquium speaker, Professor Uri Keshet from University. And so who I know very well since my PhD already in Weizmann. So who also did his PhD in Weizmann before me, then went to Vice Fellow in the Institute for Advanced Study in Princeton, continued as an Einstein Fellow in Harvard, and then came back to University, where he is since then he's still there. And so, Uri, please. Okay. The largest, yeah, I'll tell you the light. So, usually have one set, but you can't have one set.
Should I start like this?
Okay.
Okay.
No.
You prefer more dark? People prefer the dark. I'll begin and then So I want to discuss the largest features of the largest structures. And not to keep you in suspense, the largest structures we have in the universe are giant potential wells on huge scales. They're the largest potential wells that will ever form in our universe. And they act like island universes. They swallow everything around them, including galaxies, and very little except light escapes from them. We call them clusters of galaxies because they just look like bunches of galaxies together. Here's on the left you see a simulation of such a galaxy cluster, density on top and temperature on the bottom. And on the upper right you see a combination of observations of such a galaxy cluster. It's a very famous cluster. I thought this works, doesn't it?
Yeah.
I'll speak even louder. Is it okay? Do you hear me in the back? Okay. So this is the famous bullet cluster. It's actually two such potential wells colliding with each other on huge scales. So the distance between this potential well, which you see in contours, and this potential well is something like 2 megaparsecs, 6 million light years. So I'll use this astronomical definition of 1 parsec, which is 3 light years. So the scale here is megaparsecs, millions of light years. So the largest features, so I should say these clusters are very important to us, and they're very useful in astrophysics. They're good cosmological probes. So their abundance, for example, is sensitive to the mysterious dark energy component of the universe. They provide us with a rare opportunity to see dark matter separating from the normal baryonic matter. So these potential wells are dominated by dark matter, but the normal baryonic matter has been stripped away from the potential wells in this collision. So this is a very nice visual.
Could you explain what these potential wells are?
These potential wells are, the way we see them is by, we image them is by looking at weak lensing, at the lensing of galaxies in the foreground, and we see how they are distorted by gravity as the photons propagate from the source galaxy to us. So these contours are a complicated reconstruction of the potential, the gravitational potential on the way to us. They are dominated not by, so in colors you see X-ray gas, you see most of the matter, the baryons. And they are not, do not coincide with these potential wells. And so this is one case out of many in astronomy where we see that there's mass missing and we need to add another component, a dark component, which we call dark matter for lack of a better understanding. And so they're also very good not only for cosmology and astrophysics, but also for plasma physics. I'll show that there are some interesting collective phenomena taking place here. The largest features of these clusters are arguably their mysterious edges. So we think that there should be a very sharp transition, you can see it especially in the temperature, between the clusters and the region outside of them. This is where we think very fast supersonic flows of matter fall into the potential well and are suddenly and violently stopped and thermalized, and they are heated to nearly virial temperatures, so we call these virial shocks. They're interesting phenomena, and the problem is that they're notoriously difficult to find. So one of the reasons is that the densities in these peripheral regions are very low. There's hardly any light coming from these regions. We can image the centers very nicely, but not the peripheries. So people have spent decades looking for these shock waves because they're important. They define the cluster. There's a bunch of interesting physics going on there. And what I want to show, if I have time towards the end of this talk, is that we've been able in recent years to find these shocks. And this is one example of a 6 sigma detection of these shocks in gamma rays using the Fermi satellite. This was a work led by Igor Rice, who is graduating this year. So I was asked to give a hefty introduction. So I'll introduce structure, large-scale structure in general. And then I'll introduce how it evolved, and only then the virial shocks and the theory. And with whatever time I have, I'll discuss the hunt for these virial shocks and why we think we succeeded finally in doing it. So a good place to start is the beginning, the night sky. So as you know, there's a bright stripe on the sky known as the Milky Way, which we think is just the accumulated light from many stars, consistent with us, with the sun being inside a galactic plane of stars. So allow me to unfold this spherical picture on the board, keeping the Milky Way at the equator, like so. We can decompose this bright Milky Way into individual stars. For example, this is the nearest star, Proxima Centauri, this red dot here. It's only 1 parsec away, that's 3 light years. It has a planet even, an exosolar planet, and new technology is now being developed to send satellites there. But this is a tiny object, so here I plot scales just to give you a sense of how the size of the objects I want to describe. So Proxima Centauri is somewhat smaller than our own sun. So this is a logarithm of mass in units of our sun, solar mass. So I want to go to larger scales, but that is going also farther in distance. So 4 orders of magnitude farther out, we reach the center of our galaxy. Centers of galaxies are notorious for harboring supermassive black holes, and our galaxy is no exception. So there's a supermassive black hole right here. It's called Sagittarius star. It's 4 million solar masses, and we can measure its mass pretty accurately simply by following these trajectories of stars. This video is over a span of some 15 years. So this is larger but still far small compared to what I'm interested in. So we have to go outside the galaxy. So let's go 2 orders of magnitude farther out in space. We then reach our nearest large galaxy neighbor. It's called Andromeda, or N31, and here's an image of it. It's a galactic disk which looks, we think, pretty similar to our own. It's possible to show that this disk is actually a small fraction of the mass. This is the stars are concentrated in the bottom of the potential well, but you can measure that there's actually a much larger potential well filled with gas and mainly dark matter. And the scale here is a million light years side to side. So the actual disk is much smaller. It's this small thing you see in the center. So this is a larger object. We jumped another almost 6 orders of magnitude to a galactic scale. But I want to discuss clusters of galaxies. And we're very fortunate, in fact, suspiciously fortunate, to have a galaxy cluster smack in the North Pole, only 2 degrees from the North Galactic Pole, which is very useful because all the contamination and galactic structure is all but gone when you're looking directly to the North Galactic Pole. It's called Coma, and each point here is not a star, but rather a galaxy. So this is now 10 to the 15 solar masses, and this is the scale I want to discuss. This potential well is so deep that the gas is heated to KUV temperatures, so it emits a lot of radiation and X-rays, and our X-ray satellites can then directly show us that there's more than 10 times more mass in the gas component within these galaxies. But actually there's even 5 times more mass in this potential well than in this gas. It's in the form of dark matter, which I already mentioned. So this is gas, but actually plasma. I'll describe it in a minute. So all this is, so as you see, we can see some of the galaxies, but what I want to see is, what I want to do is get rid of the galactic contamination and see the extragalactic large-scale structure, and we can do that because galaxies fall into the potential well. So if we just look at galaxies, we can see the large-scale potential, and this is what we get. So here, each point is a galaxy. It's color-coded by its redshift, its distance from us. This is Coma, pretty near. And what you see is a sort of complicated network of interconnected filaments. These clusters form where these filaments connect to each other. So this is called the cosmic web because of its web-like appearance. And it's a very striking feature which we see on large scales. So this is a map of the sky. It's only a two-dimensional projection. But we can do this in 3D because we have information about the distances of objects from us. So this is a combination of images of galaxies. It's a zoom out from a large survey known as DSS. On the top right, you see a zoom in into a cosmological simulation. And both show this cosmic web filamentary structure persisting over many scales. The density inside these filaments and inside these clusters is much larger than the density, the mean density. I define rho bar as the mean mass density. So this is called the contrast, the difference in density normalized by the mean. And this is a very large number in today's universe because we have a very evolved structure. We are huge contrast objects. By the way, notice that the cosmic web here turned red. It started out white. It turned red simply because we're looking very far away from us, or very far back in time, so everything is redshift. So we could prepare such images by a lot of work, by identifying galaxies and mapping them. If you just image the sky, you usually find this galactic structure in various bands. This is the radial map. So all of this is galactic structure, hiding the extragalactic stuff. But there's a very important exception. There's a frequency in which you actually can see very far away from the galaxy, and that's the microwave. That's the microwave. And here's an image that people don't show enough. I think it's amazing. This is, of course, the cosmic microwave background radiation. This is a 2.7 Kelvin radiation, which is a remnant of the Big Bang. It's been propagating to us uninterrupted since the universe was at redshift 1,000, meaning that it was 1,000 times smaller than it is today. So when the universe was that young, there was no structure. I mean, if there were galaxies here, we would see something instead of this very uniform map. So the contrast here to these percent levels shows nothing at all. Not a galaxy, not any other structure. You have to dig very deep into the signal and get into resolutions of 10 to the minus 5 in order to see that there actually is some primordial structure when the universe was so young. But it's very minute, so it's a constant density with small 10 to the minus 5 fluctuations. And the question is, of course, how do we go from having such small contrast, minute fluctuations in the early universe to all the complex, high contrast cosmic world we have today? This is the problem of structure formation in the universe, which I want to discuss now. So, of course, the driving mechanism, as you might expect, is the gravitational instability. But I think before I go into that, I should give one slide to remind you of what's the physics on large scales and what is the lambda CDM model. So let's build a model of the universe. So obviously we need gravity. So here's Einstein's equation. We actually, to describe, this is the potential well which one day will become a galaxy cluster, for example, of scale lambda. So we actually don't need general relativity, GR, to describe this potential because it's fairly shallow. The scale here is much larger than the Schwarzschild radii. So I can do pretty well with just using Newtonian gravity to describe these structures. The GR correction will be tiny. I do need GR to set the frame, the background of an expanding universe. So this can be done with the metric in our homogeneous isotropic on large-scale universe. It's very simple. It looks like a Minkowski metric with this expansion factor, which we call the scale factor, which just causes the metric to inflate in time. So this is the only thing I want to use from GR in this talk. The universe, as I mentioned, the radiation was 3 Kelvin, so all the interesting action that we had in the early universe, all the standard model, baryogenesis is all but over. We only have first generation fermions, and in this talk I actually only want to discuss electrons and nuclei interacting by this QED diagram, electromagnetic diagram. Which nuclei? So the universe is not dense enough to generate anything heavy, much heavier than helium. So we only have hydrogen, which is 75% by mass, helium, which is 25%, and only trace amounts of heavier nuclei. So it's a very simple chemistry. These potential wells, as I mentioned, are hot, they're about keV, so obviously everything is ionized. We have plasma. And this plasma behaves as a collisional medium. The reason is that we have electromagnetic collective modes. They play the role of interaction, and they operate on very small scales compared to the scale of the object. So we can use a fluid approach to analyze these structures. So I can just use the fluid equations, the continuity, Euler, and energy equations, and describe everything in the fluid approach in most of the units I care about. But there's one important thing to notice is that these collisions, these interactions are not mediated by binary collisions, by strong Coulomb collisions. It's collective electromagnetic modes, which, as you know, give rise to interesting, unexpected physical phenomena. So this is called a collisionless plasma because the binary collisions do not play an important role. The infrared gap is huge. There's one simplification which I'll use, and that is that the velocity fields are approximately irrotational. The reason is the vortices that you have in the early universe die out because as the universe expands, angular momentum tells you that these will slow down. So I can approximate the velocity field as just the gradient of some scalar function. I'll use that later. So this is the model. Does it describe the universe well? No, because we're missing a lot of mass. So we need to add some mass. So this is this dark matter, which could be, for example, some very weakly interacting massive particle or WIMP. So we need dark matter. And it cannot be very relativistic in the early universe when galaxies form because it will kill the galaxies. We wouldn't have galaxies. So it has to be cold. Now this almost works, except the expansion, the accelerated expansion of the universe. To do that, we really need to modify gravity somehow. For example, by reintroducing the cosmological constant into Einstein's equation. And now everything gives a fairly good description of all the observations we have. There are some exceptions which are interesting in my hint at physics beyond this model, but for the most part, I'll focus on this lambda CDM, lambda just because it's the cosmological constant, it's cold, C, and dark matter. So I hope this is familiar to you more or less. And now I can go back to the question I'm interested in. How do we go from this very subtle structure to the structure we have today? And why do we have a cosmic web? Why is large-scale structure? Why does it look like a web? So the engine for driving these structures is a gravitational instability. If you have some potential well, it will grow. Imagine, for example, you have some massive particle around lower mass particles, and they will be attracted to this. It will fall down this potential well, and the potential will grow deeper, and the object will become more massive. It's an instability, it's a runaway process, and if it would be allowed to run free, it will turn a homogeneous universe with only small perturbations into a very lumpy universe of fluid structure, until something stops these structures from forming, and what can do that is obviously pressure. So it's a competition between gravity pulling in structure and pressure trying to resist. And so you can compare the typical time scales. This is as usual, the time scale for gravity is 1 over the Newton constant times the mass density, 0, square root of that. And the pressure, on the other hand, has to communicate information across the structure, so you need, so the relevant scale is the sound crossing time. So CS is the speed of sound, and depends on the structure of this object. If you equate these two time scales, you get a characteristic length scale known as the gene scale, which just tells you that if you have structures which are much larger than that, pressure doesn't have a chance to resist, and these will collapse and form objects. But smaller objects will just oscillate because pressure will have time to counteract gravity. So I cannot do actually I don't have a code here, so I cannot do a demonstration of the potential wells, but I can do a demo with bubbles. I have a video doing the potential model. So if you just reverse the direction of the potential, instead of potential wells, we have a surface of a liquid with some bubbles. So a bubble, like this green bubble, will lift the surface, and nearby bubbles will be attracted to this bubble. So again, we have an attraction, although I flip the sign of the potential. So what I can do, not today, is take a bottle of Coke, shake it, pour it into a cup, and then just hit the table with the cup. And this causes many, many tiny bubbles to form on the surface. So this is sort of my analog of the initial universe. And actually there are already, if you have sharp eyes, you can see that there are some accumulations of bubbles which will someday turn into bubble clusters or super bubbles, whatever you want. So this is what happens. So it formed all kinds of structures, and now you have mergers. You see the small bubbles became larger bubbles, and now they're merging. And if you have sharp eyes, you could notice that there's actually a cosmic web forming there. Let me freeze this and try to highlight the web. So there is a web structure forming here. So bubbles are lined along filaments, interconnected. This is at the later time. Again, I'll highlight this, and hope you can see that there's a web forming here. At late times, we have these kinds of mergers, which are sort of resembling the bullet cluster, which I showed earlier. So at late times, there are non-linear processes like this. So the question is, why does a web form in the universe? And why does it form in a glass of Coke? The answer, one way to see the answer is with the Zel'dovich approximation. This is just the first order perturbation analysis. We're not using Eulerian coordinates, which are fixed in space, but rather Lagrangian coordinates, which are stuck with the fluid. So Q is my Lagrangian coordinate, R is the Eulerian coordinate, and this is the relation between them. This A just takes into account the fact that the universe is expanding. It's not so important. Structures grow because this instability causes them, the potential was to become deeper, and it can be shown that it's a power law in time. It's not an exponential as you usually have when you have an instability, and the reason is that you have to compete with the expansion. It's a power law. This S is just the flow field, which I already argued is irrotational, so it's just the potential of some function. So we can compute the density evolving in time. The density in Q space is fixed because the coordinates are stuck to the fluid, they just move with it. So we can just get the actual density in Eulerian space by this Jacobian, which then depends just by using the first equation. It's just the determinant of this function, and you have a second derivative, which is obviously symmetric in the two coordinates, so we can diagonalize it, and we can just have, so this matrix is just, you can think of it as a principal axis matrix where lambda 1, lambda 2, lambda 3 are the eigenvalues. And in general, they won't be the same. When I say that lambda 1 is the largest and lambda 3 is the smallest. So I'm just rewriting this equation, and this immediately tells you that you're going to form pancakes followed by filaments followed by blobs, because as B increases in time, the first term to become very small is the first one, the lambda 1 term. So at this stage, we will have a two-dimensional object, which we call a Zel'dovich pancake. At a later time, the second term will also become very small. So now the two axes have collapsed, and you have a filament, and only at late stages, all of these axes will collapse and you get a halo. At late times, you get nonlinear evolution, which includes mergers, fragmentation, etc. So this is the basic picture, and it also works on Coma. So what kind of structure does eventually form? So consider some primordial perturbations. Let's say that we have large perturbations in green and small perturbations in yellow. And say that the potential wells on small scales are more evolved. There's more power in them. So here I plot the power spectrum. How much power do you get in each scale? And in this specific example I made up, the small scales have more power. So in time, in the linear stage, as usually happens, everything grows uniformly in Fourier space. So we just, all potentials become stronger until they become nonlinear. And once you reach nonlinear stages, this contrast becomes one, the evolution becomes very rapid, and very quickly you break out, and these small objects, which had a 4 on the others, break out and form virialized objects. So small structures will appear first in this case. We could, of course, have the opposite case, where we have more power on the small, of the large potentials, and they're more evolved. They will have more power, they will grow and break out sooner, so we have large structures appearing first. And the question is, which happens first? What happens in our universe? By the way, I don't actually need to make the power spectrum increase in time. You can just plot the fixed power spectrum and just lower the bar in time to see which becomes nonlinear first. So what does our universe do? And this allows me to show this slide, which is my favorite slide in all of physics. This is the power spectrum of our universe. You see here this contrast square as a function of, I think I told you that. It's good to have you guys have a backup. This is scales a billion of light years. Here you just see this gravitational instability in action. And what you can see here is that we have more power on small scales and gradually less on large scales. So this was like the first example I showed earlier. And this is a threshold evolving in time. So what you can see is that we first form our universe happens to form small galaxies first, then larger galaxies, then clusters, then superclusters, and happily or sadly, at this stage everything dies because the universe started to accelerate its expansion, and this entire story is over. We can no longer form linear structures in today's universe. Let's see this. 5. Yes, okay. So it took, by the way, many thousands of years of human work years to generate this kind of thing. So now I can finally reach virial shocks to discuss how specific. Let's focus on one such object and discuss how it forms. So this really depends if you have a collisional or collisionless medium. So if you have a collisionless medium, for example, a non-interacting dark matter particle, you just have a bunch of particles that can cross each other's trajectories. So let's start with some potential will and just let them fall in. And what will happen is diving. Okay, that was supposed to be good. Oh, hopefully it will not. So they will just fall in and they will begin to fly across each other and they will, last time? Okay, now it works. So they fall and they sort of begin to travel inside this potential well, and this green line, green circle, is a radius in which the density of these particles suddenly increases. So there's many more of them inside. This is called the splashback radius, and actually people have claimed in the past few years to identify this splashback radius in observations sensitive to dark matter. However, I'll focus mainly on the collisional medium. So here you can not have fluid elements just flying across each other. So what you have is fluid coming in, being violently stopped. This is a shock wave, it's an accretion shock. So the shock is propagating slowly outward. The reason it's a shock wave is that the matter that's flying in is flying supersonically compared to its sound velocity, and it's stopped and heated inside. So the density on the left, you see it's very centrally concentrated, but there's a well-defined large bubble which has this sharp edge, which is the virial shock I'm looking for. And this happens in the collisional medium, although as I mentioned, these collisions are not binary collisions. So this was introduction. Now I want to describe the hunt for these virial shocks. This is why do it at all. So there's several reasons. First is we want to test the structure formation theory, which I just briefly explained. These virial shocks trace the large-scale structure of the universe, so they're very useful cosmological probes. Most of the things we see in astronomy are fixed in time. I mean, if your grandchildren will have an image of the bullet cluster, it will look very similar to what we have today. But these shocks are very sensitive to the rate of flow across them, so they're dynamical tracers, which are very useful. There are some interesting connections between the virial shocks and the splashback radius. It can tell us something about dark matter interactions. These virial shocks actually do emit some radiation, which could provide an interesting background field. And there are, of course, many other reasons. But for me, the most interesting reason to study this is that these shocks provided an excellent laboratory to study shocks in pristine conditions. Let me explain what I mean. Especially the acceleration and acceleration of particles and magnetization of the plasma. So it's well known in astronomy that collisionless shocks, these kinds of shocks, which are mediated not by binary collisions, accelerate particles. They're natural particle accelerators. So it's often useful to think of a shock as a waterfall, and image it as a waterfall. So we have, this will be the shock. The upstream flow is a very thin layer So a small surface density of very fast moving water, and then it falls down, it becomes a thicker, we have downstream, we have a thicker layer of water, and all the oriented bulk motion became a random motion, something, we have turbulence often in these cases. So this is a nice analogy to a shock. So a real shock, it will compress the gas, it will heat it up non-reversibly, will increase the entropy, and will often generate turbulence. So here I plot the distribution of particles in the upstream medium as a function of their energy. So this is the spectrum, energy spectrum of particles, and we usually have something like a Maxwellian. What will happen downstream? So the medium is heated, so everything will shift to the right, and then also it's compressed. The density increases, so we'll get something like this. And so it's another Maxwellian, and this is what happens if you have an explosion, if you have the supersonic boom of a jet, you get this type of behavior. But this is like collisions are binary. If you don't have binary collisions, something very non-intuitive and to me very surprising happens. The power spectrum doesn't look like this, rather it looks like this. We don't know exactly what happens in trans-relativistic energies, but when you go to the ultra-relativistic energies, you get a tail of particles which seem to get more higher and higher energies, and we don't even know if this process stops, unless some cooling mechanism forces the particles to stop and not hit beyond some threshold. So we get power tails which extend to Lorentz factors of 10 to the 7, 10 to the 8 in astronomical systems. This is very strange to me. We don't understand to this day the details of the mechanism, but our basic picture is based on an idea by Fermi dating back to the 40s that some particles manage somehow to jump over this threshold, become relativistic, and then they're able to bounce back and forth from upstream to downstream and draw energy from the converging flows. This is just the basic picture. I don't have time to go much more deeper into this mechanism. I just want to point out that many astronomical systems and many important astronomical observations are based on these accelerated particles. So all the bluish emission you see here is shock accelerated particles. In fact, we think that the cosmic rays that hit the atmosphere of Earth are particles accelerated in supernovae shocks like this one. This is a star that blew up 1,012 years ago. So these are various systems that show such shocks, ordered roughly by scale. The red systems show relativistic shocks. And the reason I really care about virial shocks or structure formation shocks is that they're excellent laboratories for these supernova remnants. They're quite similar, but unlike a supernova remnant like this one, which is very difficult to model, so virial shocks are simple. The reason this is difficult to model is that the upstream of the shock, the medium that has not been shocked yet, is dirty. It has non-trivial chemistry, it has a pre-existing substructure, it has magnetic fields, whereas in structure formation shocks, the upstream medium is just this pristine hydrogen helium medium that's been falling on the cluster since the Big Bang. So it's a much cleaner system. So here's a model, a spherical Car model of the virial shock. We have some object, say a galaxy cluster or a galaxy of mass n and temperature T one day, and it's accreting mass from its surrounding. And this gas has been falling since the beginning of the universe, so we know the relevant time scale, the universe age. So you can immediately compute the typical upstream velocity, and it's order of thousands of kilometers per second, very much like supernova remnants. So we can postulate that it might have the same physics and also accelerate particles and magnetize the gas as well. We don't understand the mechanism so well, so we just parameterize our ignorance in these parameters. So psi e would be the fraction of energy that mysteriously is deposited in this non-relativistic, in this ultra-relativistic particle tail. Psi b will be the fraction of energy deposited in magnetic fields. Actually, when we measure virial shocks, we are sensitive to the mass accretion rate. So there's the actual parameter I'm going to measure is psi times m dot. M dot is just the accretion rate, how much mass is accumulated by the object. Its dimension is we use the Hubble constant to normalize it. Okay, so this cartoon just shows how electrons can bounce back and forth across the shock and reach higher and higher energies. How can we detect such a shock, such particles? Well, they radiate. If you have an ultra-relativistic particle moving in a magnetic field, it generates synchrotron radiation. So we expect to see radio photons from these shocks. Similarly, remember this cosmic microwave background photons, these microwave photons? they can collide with these relativistic electrons, and this is a Compton scattering. Actually, it's an inverse Compton scattering because here the electron doesn't get energy from the photon, rather it's an ultra-relativistic electron. It gives energy to the photon, and it shoots it from the microwave region band all the way to the far gamma ray band. So we get these gamma ray photons from such a shock. So we can look for both gamma ray and radio correlated signals. These shocks also accelerate protons, not only electrons. Any charged particle will be accelerated. And these protons can escape us, they can reach us in the form of cosmic rays, or they can migrate inward towards the cluster and hit some innocent proton or neutron here and generate a pion shower, which can then generate more electrons, more photons, or neutrinos. But I don't have time to discuss all this so-called hadronic physics. I'll just focus on the electrons in this talk. And so we've been simulating these kinds of structures and these shocks for many years. This is actually my master's thesis work in 2002. So this was at the time considered state-of-the-art graduate simulation. And since then people have done much, much better. So what we see here are large-scale filaments and shocks surrounding them. The resolution is quite awful. It's been much better since. And these new simulations have been instrumental in resolving all this substructure and all the small shocks. But if all you care about is the energetics of these virial shocks, then the old simulations are fine for this purpose, so I'll use them. So this is actually an image which shows radiation ignoring all of astrophysics except these virial shocks. So this is what you would see in gamma rays if you just image the virial shocks around structure forming. We prepare this for a satellite then known as GLAST, now known as Fermi. And this we prepared for atmospheric Cherenkov detectors such as MAGIC and Veritas. So this is just a zoom in on one such object, the nearest large cluster. So this will be the Coma cluster in our simulation, the one I showed earlier. And it sort of shows a ring with bright spots. And these bright spots can be shown to simply be these filaments that channel a lot of mass into the cluster and light up these bright spots. So we expect to see rings with bright spots, which are very telling. It tells something about the surrounding filaments. So here's the gamma ray spectrum we expect. It's very flat. The reason it's a log power law, it simply reflects the electrons. I showed you a flat power law of electrons generates a flat power law of photons. So this is gamma rays, this is radio. And in fact, it's the same Feynman diagram because it doesn't, the relativistic electron sees a photon and scatters it, and it doesn't care if it's a CMB photon or a virtual photon, one of those that comprise the magnetic field. So these are essentially the same process, so the ratio between them just depends on how much cosmic microwave background photons you have versus how much magnetic fields you have. So for our typical magnetization parameters of 1%, the gamma ray component is much stronger. This is an easier target in a sense. So since the early predictions of the gamma ray radio, people have pointed out that it's also possible to see this emission in X-rays, provided that you somehow manage to get rid of this huge thermal bump that non-relativistic gas generates. And this Zel'dovich effect is also very interesting. I don't think I have time to describe it today. So this was in general for structures across the sky, and now let's focus on one such object. So this is, remember this Coma cluster I started with? So we actually predict, this was a map we presented as a Coma. These simulations were not constrained, so the orientation is crazy and the location of the sky is not special, but you can actually use the actual observation of galaxies around Coma to reorient this map and produce this kind of map with the right coordinates. So this was our prediction for what someday, hopefully, observers will be able to see in the sky. So a ring with these bright spots. And actually, I left this.
What is virial all the time that you are? What do you use the virial theory?
So
equipartition between magnetic field.
Sorry, I probably skipped that. So it doesn't matter if you have a collisional or collisionless medium. In both cases, once particles fall into the potential well, you heat them up, and the virial theorem tells you that the kinetic energy is comparable to the potential energy. This is the virial theorem. It's in the case of Newton's law, it's half. So these
you don't
shots,
have to put it in.
I don't
The real
put it in.
theorem,
I'm not
the
putting
real
it in.
theorem, if you do correct physics, then the virial theory is there.
Absolutely, you're absolutely right. And this is what happens. So if there will be a supersonic boom in this room, it will not virialize us necessarily. But these shocks are very strong. They virialize the temperature. The gas is heated to a temperature which self-consistently must obey the virial theorem. And that's why we call them virial shocks. You can call them structure formation shocks. But it's the same idea. They convert bulk flows into random flows which have the virial temperature as you would expect. Okay, it's just the name. I was saying this was my master's work. I abandoned. I left it there in 2002 and went to do other things. I never thought I'd go back to this problem. But when I came back to PGU 10 years later, this map was published from Cherenkov atmospheric detector called Veritas. This is a map with 220 GeV. And this just immediately reminded me of this initial prediction because it really seemed to me like it's the missing piece of the puzzle. And I was hoping that this might actually be the first virial ring detection. You have to be careful and translate this map, which is actually some test statistics map, into a flux map. But after you do that, it doesn't look very different from this map, and it correlate very well. So it's a 3.7 sigma correlation between these two maps. So I was very happy. I thought maybe it's a first signal. You can also quantify what's the probability there is. You can just throw Monte Carlo simulations, throwing random noise, and see what's the chance of getting something which in my eyes looks like a ring here, but I know I'm biased. And you get something like a 2.7 confidence level, but this ring is exactly in the right location. It's in the radius, which we call the virial radius, because that's where these shocks are supposed to form. But in fact, those of you who work with Cherenkov detectors, they're notoriously difficult due to the foreground. You have to work very hard to subtract the signal from itself to get rid of the foreground. So what the pipeline of the observation does is kills any extended structure. So in fact, it's almost impossible to get these kinds of extended structures in maps. We had to simulate many millions of them to show that it's actually a 5 sigma signal to get by chance such a signal resisting all the pipeline corrections that were made by this Veritas collaboration. So I think this is actually a discovery. It's a crucial parameter, the acceleration efficiency parameter, which was completely unknown, is 0.5%. We were optimistic and thought it would be 5% when we were 10, 15 years ago, but it turns out it's less powerful. These shocks are less efficient in accelerating particles than we thought. But we only published this as a preliminary signal because the systematics here in the peripheries are really, really difficult to handle and not well tested. Having said that, I should point out that it's very suggestive because we examined many such mosaics from Veritas. None of them showed such signal. There are various other indications that the signal is real. For example, this is a gamma ray image, but it correlates with the radio image shown here. So these yellowish regions are regions where there is a correlation. Red is radio, green is gamma ray, and yellow is where they correlate. And so this is like 3 sigma correlations with radio, with Zel'dovich signal, which I don't have time to explain, etc. I was very happy because I was always told that the good astrophysics theoretician should make a prediction that is tested within a decade. This was exactly a decade after the original papers, but the referees were not excited, and it took actually 5 years to publish this work. So for those of you struggling with referees, it could be work. So as I think you can be convinced from this story is that it's difficult to look at one object, which is very messy, a lot of noise and pipeline complications, and argue that there's a signal. Can we do better by looking at many of them, using the fact that we have a large number of clusters on the sky? So this is a stack. Yes?
Can you say a few words about Veritas and you have the 220 GeV there? So 220 GeV is what exactly?
220 G. So the Veritas experiment is, I think, 4 or 3 dishes, large dishes, looking at the sky, looking for these 220 GeV photons reaching the atmosphere and generating a shower of particles, but some of which generate Cherenkov light, which happens to hit inside the dish.
And
So
is that just looking specifically at 220 GeV, or that's what it's?
no, it's looking at some position on the sky for many, many hours, many nights without the moon, and it's collecting all the Cherenkov lights, and it has a fairly broad sensitivity in energy, but it's peaked at 220 GeV for this specific. They can play with it. They can change the settings and their analysis to be sensitive to slightly shift the energies, but they're always on around a few hundreds of GeV. Is the range. So here I show you this initial imagery with this prediction where each circle here is the galaxy cluster. It only gamma rays from virial shocks. This is the actual image from Fermi. We block the galactic center because it's very contaminated, and every circle here is a galaxy cluster. And what we can try to do is look at all of them together, combine their images, and try to get rid of the noise and strengthen the signal. The problem is, of course, that every cluster is a different animal. So here you see the pressure versus radial versus radius of different clusters. Each line here is a different cluster. So they're different beasts. But there's a self-similarity, a well-known self-similarity here. You can rescale the radius by what we call R500. It varies between clusters, but it's of order of 1 milliparsec. Each cluster has a different radius. We know how to measure it, and we can normalize the pressure as well. And then all of these clusters, all of these lines collapse on one, not in the central regions, which are messy, but in the periphery, they more or less collapse on one line. And if our theory is correct, then if we have the sensitivity to go further out at some point, well, I'm out of board here, but here you should see the pressure suddenly dropping because this is before the shock. This is the upstream and this is the downstream of this shock. So we've been looking at this. So once you have many, or after you renormalize this way all the maps, you can put them one on top of the other. This is called stacking. It's by no means specific to astronomy. It's applied to many fields. But the idea is that if you have various structures, every one of them has a slightly different morphology, they're ellipses. If you stack all of them, you'll get something like a ring, which is the common denominator of all these structures. So this has been applied to many fields. For example, this is a stacking of many faces of Israeli males and females, rescaled to match in proportion. And if these guys look familiar to you, then this method works. It's a very common method in astronomy. This is just stacking papers from a typical month. This has been attempted many times. People have applied it to various data sets, Egret at the time, Fermi, nowadays, and except for one false detection, which was actually a mistake from the early 2000s, there is no signal detected by this method. It was not successful. But the problem is that none of these works were really targeting the virial shocks, so they did not bother to rescale the images. It's like stacking many pictures of male Israelis without changing the dimensions of the image. So when we did with normalization, we get this 6 sigma detection, which I mentioned before. We also had the advantage of slightly better data and more data from Fermi. I don't have time to describe, I think, the Fermi satellite, and I'll just skip to the result. So here you see the stacked line. This is the R normalized by this R500, or megaparsec, and here you see the significance of the excess of the flux above the foreground. And you see that there are two peaks here. This peak is a well-known point source. We know that these clusters tend to hide a massive galaxy in the center of the potential well, and that potential and these galaxies hide a supermassive black holes in their centers. And this is just jetted radiation from these so-called lasers inside the massive galaxies inside in the center of the potential well. These are point sources. We were very good at removing them from the data. So this is not the structure, and this has also been known before, but this peak is new. It's a 6 sigma detection. This is just the shape of our foreground. So this is a very strong detection. It was, this is actually the image, the stacked image, and this pinkish radiation is the ring. Of course, you really need to do radial baking to see it clearly. Otherwise, it would have been a nature paper, not an object paper. And here we see the parameters of the model. This is the radius of this ring, again normalized. And here you see this psi e and dot, this parameter, efficiency of acceleration, which I'm measuring. This red band is where we expected the shock to be. indeed in theory, and indeed these are different. These circles are 1 sigma, 2 sigma, 3 sigma confidence intervals for different variants of the model. They're consistent also with the Coma measurement, which I showed earlier. So we think that the acceleration efficiency is like something like 0.6%. Lower than we expected, but we don't really have a theory yet for these. Nobody knows how to compute this acceleration efficiency from theory to this day. So this is the efficiency, the spectrum I mentioned. If you remember, I showed a very flat spectrum, but I was plotting e squared times n. So the spectrum actually goes as e to the minus s, e to the minus 2. Usually it's 2.2, and this is indeed what we see. And I should just say that we were extremely conservative in all this analysis. We used binning and very traditional methods. If we actually relax our assumption and use all the information we have, then the detection significance jumps to 11 sigma. But we were very